Hello there, this is my first video. In this first video in the series of Matlab lectures on digital signal processing. In this video I'll be covering basic digital signal processing subjects like signals and systems. So we'll begin with concepts of signals and system in discrete time, and also emphasizing in this lecture I'll be emphasizing in this lecture representation implementation of signals and systems using Matlab. So let's get started. So discrete time signals will, as you know, they are denoted by x, small x of n, in which the variable n is an integer valued and represent discrete instances in time. Therefore, it is also called discrete time signal, which is a number of sequence, and it's basically denoted by this notation. The arrow within the sequence, for example, in this slide, x of n is it may vary from x of minus 10 to x of plus 10, and the arrow signifies the time 0, or where the time vector starts. Basically, signals are broadly classified into analog and discrete signals. An analog signal will be denoted by x of a into bracket t bracket close, in which variable t can represent any physical quantity. It can be time as well, but we will assume that represents time in seconds. In discrete signals, it will be denoted by x of n, which is the variable n is integer valued and represent discrete instances in time. And where, like I said, where the arrow indicates is the sample number 0, or where the time actually starts. So moving forward, in Matlab you can represent time by a plot. I've covered these plots in previous sections. So we'll be implementing this equation, which says x of n is 2 of a impulse sequence n plus 2 and minus impulse sequence minus 4, and the n varies between the limits of minus 5 and 5. So the number of samples are the range is minus 5 to 5 in time, like I said before, and we'll be implementing this equation in Matlab. So let's see how it is written in Matlab. So first of all, like before, I'll create a linear vector which will vary from minus 5 column plus 5 bracket close. So you can see n is now a single row vector starting from minus 5 to 5. Now I'll implement the equation. So small x is equal to 2 multiplied by impulse sequence. This is an inbuilt command within Matlab to create impulse sequence, bracket open, minus 2 comma 5 comma minus 5 comma 5 and bracket close, and I'm subtracting another impulse sequence from this sequence 4 comma minus 5 comma 5 bracket close. Impulse sequence. So to give you an idea what the impulse function is, I'm gonna show you the code so that we can understand what we are making over here. So impulse function basically takes a number of sequences and outputs x and n values So the impulse gets 3 functions n0, n1 and n2, and generates the impulse at the location defined. So let me let us do the example again. So first of all, I created a sequence n, then the formula that will create impulse functions on the n sequence, and then I'll plot a stem function of this plot. So here you see it has created 2 impulses at -2 and 4. So this is another way of plotting impulse sequences in Matlab. Okay, so sorry. Okay, so this was about impulse sequence. Now we'll talk about something about discrete systems. In DSP, we will say that a system processes an input signal into an output signal. Discrete systems are broadly classified into linear and non-linear systems. In the next slide, I will explain to you what a linear system is, and then we'll do an example of linear systems. So this is an equation of a linear system. The solution, the way this function, this equation represents, will determine the response of each system in a linear combination. So a1 y of n is t denotes time into x of n is equal to 3 into 2 n vector or matrix. So there are many ways to represent non-linear linear systems in Matlab. Let us see what Matlab gives you, how to represent them and how to plot their responses. So we will first go through convolution. So convolution is one of the properties that we're gonna do in Matlab. So convolution within the LTI or linear time invariant system can be described as a response of LTI system. In DSP, it is important operation. It has many other uses as well. Convolution can be evaluated in many different ways. If the sequences are mathematical functions of finite or infinite duration, then we can analytically evaluate for all n to evaluate a functional form of n. Basically, convolution tries to match the filter response or impulse response against a sequence, and it multiplies with each sample, and as it goes through all of the values of the magnitude of all the signals is combined together. So I'll show you in Matlab how we can use convolution. So for example, I'm gonna create a signal. I think I did that. It was x, which n, -5 to 5. So I'm gonna create s is equal to sine of n. Okay, and I will convolute. I will create another one, c for cosine of n, and okay, so n is equal to convolute. So I'm matching these two sequences, convoluting these two sequences together as c. Okay, now I'm gonna plot n. So this is my output of convolution. Let me show you what did the s look like. So s was a simple sine wave, okay, and cosine or a simple cosine, and when you convolute both of them together you have n, which we have already plotted, and which is this. So this is your you're convoluting sine wave with a cosine wave, and this is a response, and you just need to use CONV bracket open first sequence and second sequence, and then the MATLAB will give you an output of convolution. So in MATLAB and also in DSP convention, the convolution is denoted by a star asterisk. So x of n, when you're convoluting with x of n, which is your filter coefficients, any filter, high pass, low pass, or band pass, this is the way you write an equation. Over here the sample x of n is defined as 3, 11, 7, 0. 0 is the 0 sample at the time 0, and minus 1, 4, and 2, and the samples are spread across the range of minus 3 to 3. Here is my filter response or impulse response, and its values of n range from minus 1 to 4. So this is the plot which shows the plots of impulse responses. So the top left plot shows x of k and h of k, the original sequences. The top right plot shows x of k and minus h of k. So what I've done is I've folded off or reversed h samples into minus. So the top right over here, this is with h of k, and this is of h of minus k. So with the minus k, the signals that were in positive, like it has been folded. This part has come over here. The right hand side of the first graph has shifted towards left hand side on the second graph. And when you subtract minus, you shift the signal, so it has shifted towards my left. So the bottom right plot shows x of k and h 2 minus k, the folded and shifted by 2. That is a version of k, that's the impulse response. So this was a little tutorial about how impulse responses can be plotted in a shifted version. This is a small example about convolution, and what I've already shown you how to compute convolution between two sequences. Say x is a sequence of samples that you have, and h is your impulse response, and you want to convolute two of them together. So the most logical and most simple syntax is y is equal to conv h comma h, x comma h bracket close. So okay, so we are going forward to discrete time Fourier analysis. So when a system is linear timer, only one representation stands out the most useful, and it is based on complex exponential signal set e to the power j omega n, and it's called the discrete time Fourier transform. So we have seen how a linear and time invariant system can be represented using its response to unit sample sequence. This response, called the unit impulse response h of n, allows us to compute system response to any arbitrary input x of n using the linear convolution. This convolution representation is based on the fact that any signal can be represented by linear combination of scale and delayed unit samples. Similarly, we can also represent any arbitrary discrete signal as a linear combination of basis signal. Each basis signal set provide a new signal representation. Each representation has some advantages and some disadvantages depending on the type of system under construction. So this is an example of how to compute discrete time Fourier transform. Since e exponential e to the power j omega is a complex value, we will have to plot its magnitude and its angle, or the real and imaginary part, with respect to omega separately, to visualize to visually describe x j omega. Now omega is a real variable between minus infinity infinity, which would mean that we can plot only a part of x j omega function using Matlab. Using two important properties of discrete time Fourier transform, we can reduce this domain to 0 and pi interval for the real valued sequences. We'll discuss other useful properties of j omega in the next section. So this is the formula for computing discrete time Fourier transform. You have this sequence of signal 1 2 3 4. Arrow denotes the 0 signal, and this is basically your discrete time Fourier transform. It's a summation of e to the power j omega being multiplied with all the samples except for the 0 sample. So this is the code for representing discrete time Fourier transform. Let's run this code and see what happens. So I'm gonna open a new script file. So discrete time transform. So I'll just put a comment. This is to compute DTFT. Okay. So first I'll create a series, column 1, column 500, pi divided by 500. So the x-axis is divided into 0, pi. Divided into 501 points. Okay. Next, this is the frequency component. We are calculating the frequency domain signal over here. J multiplied by, this is omega, W is omega. Okay, omega exponential j multiplied by omega minus 0.5 ones. So it will generate a number of ones from 1 to 50 points. So this whole has to go into a bracket, okay, and then semicolon you have to put in the code. So magnitude, we are calculating the magnitude of our frequency component. Absolute value of x This was to calculate your magnitude. Okay. So we are gonna angle x is equal to angle now real part of x is equal to real of capital X. Okay, now imaginary part of x is equal to capital X has to be capital. This one also has to be capital X. Okay, now creating subplot. Two comma 2 comma 1 bracket close, plot w divided by pi comma mag of capital X Okay, I'm gonna put the grid on. Okay, so X label is equal to frequency in pi units. Frequency in pi units. Okay, and title magnitude part. Okay, Y label magnitude. Oh, two commas in there. Y label, then you have subplot 2 comma 2 comma 3, and we are plotting the angle of x. First we plotted the magnitude, and now this is angle. Angle x so X label frequency in pi units. Title will be angle part, and y label will be in radians. Now another subplot will be 2, 2, 2 bracket close plot. Now we are plotting the real part of x. So omega divided by pi real capital X, okay, real capital X, and y label will be sorry, spelling is wrong, label will be real. Okay, now subplot 2, 2, 4 close, plotting omega divided by pi, comma, imaginary x, imaginary part of your signal, and grid is on, and then you have x label, frequency in pi units, okay, title will be imaginary part, and y label will be imaginary. So this is our whole file. I'm gonna save it as discrete time Fourier transform, DTFT. Okay, so let's run it, and here you go, you got 4 plots, and it's computing your imaginary part, frequency in pi radians, real part, magnitude and real part, real and imaginary part, and magnitude in radians of your signal. So you can change your signal to whatever signal you want. For example, we created omega over here. I can change omega and see what happens. So omega was okay, let this be n. So sine of n. So this is your magnitude part, radians, real and imaginary parts, frequency in radians of your sine signal that I generated from here. Okay, you can this signal can be combination of sine plus cosine and and it can be a scaled value with an amplitude of 2. So let's see what happens. So here you go, the magnitude has spiked at 0. Same is the case for this one, and frequency in pi radians, because the cosine has been added to the signal. That's why. If you convert that to sine, so you see the frequency is increases in over here. This is the real imaginary part, this is radians, and this is magnitude. So this was a small example how you can calculate and plot discrete time Fourier transform using Matlab. So this was a simple plot with simple values. Okay, so now we are shifting to Z transform. There are two shortcomings to Fourier transform approach. First, there are many useful signals in practice, such as U of n and Nu of n, for which the discrete time Fourier transform does not exist. Second, the transient response of a system due to initial conditions or due to changing inputs cannot be computed using discrete time Fourier transform approach. So now we consider the extension of extension of discrete time Fourier transform to address these two problems. The extension is called Z transform. It's bilateral or two-sided version, provides another domain in which larger classes of signals or sequences can be analyzed. It's a unilateral, that is one-sided version, can be used to obtain system responsive initial condition or changing units. So this is an LTI system, linear time invariant system, and in this we'll just plot this and see how you can compute this. It will create this same magnitude of your system, and it will create both the magnitude response of your signal. So let's do this. LTI systems. Okay. So I'm going to plot this one and see how it is computed. I'm going to create a new script file. So the first line is basically creating the omega, or just a sequence of your signal, which is from 0, starting from 0, increment of 1 and go to 500, multiply by pi divided by 500, and the h will get the frequencies, which is this is a inbuilt MATLAB command to compute both your frequency response of a system or signal. So it will basically compute that. It will create magnitude, response, frequency response of the parameters that you pass it on. So So magnitude, mag h, computes the absolute value of h. Phase will compute the angle of h, and subplot will divide your plot. Grid will be on, and I'm labeling x axis, y label will be magnitude. So I'm just editing this so that you can understand in one line what is happening over here. The y has been labeled phase in pi units, and the title will be phase response. Okay, everything is the same. So I'm saving it as LTI systems. So once again, I made some changes in this example. It was wrong. So from top line, W is just a sequence of signals, and H will get an exponential of J into omega, which is our W, divided by exponential value of J omega minus 0.9 and into ones. So let me go back to our presentation. So this was our equation: 1 minus e to the power minus j 2 omega divided by 1 minus 0.8. So this is our equation. We're gonna save it, run it, and our plot is over here. So this is our plot: an LTI system magnitude response and its phase response has been plotted by Matlab. So you can see it is in frequency in pi units, and phase is also frequency in pi units. So this is how you can compute responses of your LTI system in Matlab. Okay. Okay, so this was about LTI systems, their response. Now we are going towards inverse of a Z transform. We are going to find inverse of a Z transform of this equation, x of z, where z is divided by 3 z square minus 4 z plus 1. So let's do this example in Matlab. So just to give you a revision of how you do that, basically you are simplifying this equation by taking 3 from denominator as common, dividing all the values in the denominator by 3, and you get to this stage, and then to this stage 1 by 3 z minus 1 over 1 minus 4 by 3 z minus 1 plus 1 by 3 z minus 2, and then you simplify the denominator or factorize it into two factors, 1 minus z 1 minus 1 by 3 z minus 1, and you further factorize it, and it comes into this type of equation. So the region of convergence here, the poles are on the interior side of region of convergence. We have used that equation to plot zeros and poles on a z plane, and it shows what the response of the system is. So this is just about a revision of about how to draw the response of a system using Z transform. To implement in Matlab, let's go ahead and do this example. So okay, so in order to do this example, we'll create first system like numerators and denominators. So b is equal to 1 and a is equal to polynomials. Okay, 0.9 comma 0.9 comma minus 0.9 and square brackets and close. So these are your polynomials. Now I'm gonna calculate the zeros and poles for this. So R, capital R, comma P, comma C is equal to residues So just to revise that, what does this command does? Residues. Okay, so here's your Matlab help for this command. Residues is a Z transform partial fraction expansion, because our equation was in fractions, so I've used this function, and it finds the residues, poles and direct terms of the partial fraction expansion bz over az. So if you have a Z transform equation, you can use this to solve your partial fraction expansion, and it will return you back the number of poles is n, length a minus 1 is equal to length r is equal to length of p. The direct term coefficient vector is empty if length of b is less than length of a, otherwise length of k is equal to length of b minus length a plus 1. So this is a short, very short, efficient way of calculating that. Now so it has calculated the roots of your fraction r, p and c. Okay, now we are gonna do another example, but this time it will be using Matlab Simulink. So in this example we will be plotting the FFT of a sine wave, and what we'll do is we'll convert from time domain to frequency domain and plot it. So in the model, the sine wave will be generated into frame based sinusoids. One is 15 Hz and one is 40 Hz, and the sinusoid are summed point to point to generate combined sinusoids. So let me show you what my model will look like. So this will be my sine wave generator, row sum, then you have FFT, and then you have complex to magnitude, angle, and then you have a vector form. So the Simulink is taking long to load. While it's loading, let me show you. Okay, so here's my Simulink. Okay, so I'm gonna go into create new model, and my new model is here. Okay, create, save it as FFT model. Okay, so what I need in this is signal sources, sine wave, no, not from here, but from the DSP library. So I'll go into DSP, tool systems, then you have sources, you have sine wave generator, add it to FFT model, it's going there, and then I have row sum, matrix, row sum, mathematics, math functions, math operators, matrix, linear system solvers. No, it's not there. Inversion matrix operation. So this is, it's a row sum matrix. Okay, so it's a row sum. You can always write it over here, sum. Okay, matrix sum, sorry, it's called matrix sum. So math operators, sum of elements, no, has to be matrix operation. Matrix sum, yeah, this is the one. And FFT, I need FFT signal transforms. So signal transforms will be here, FFT. That's FFT, right? Yep. Add it to your plot. And what else we need? We need FFT plot. Then we have complex to magnitude angle. Complex to magnitude angle. So math operators, complex exponential, complex difference, no. Yeah, this is the one. Add to FFT. And then we need a plot, a vector scope. So this will come into sinks or within Matlab, within the DSP vector scope. Here's your vector scope. Add it to your plot. So now open your plot. So time vector, FFT, sum matrix, and sine wave. So start connecting. Okay, now in the amplitude block, save it. In the amplitude block, double click on sine wave block. Oh, sorry. Okay, so this one opens up. Your amplitude will be 1. You can define two frequencies over here, 15 Hertz and 40. Phase will be 0. Okay, sample time will be discrete. Okay, samples per frame, sample time will be, sample time will be 0.001. Sample frame will be 128. Okay, and apply computation method, real. Okay, output complexity. Cannot be evaluated. Okay, let me see why. Oh, okay, I have to put them in brackets. Sorry, square brackets. There is. Apply. Okay, now click on matrix sum, double click on that, sum along sum in the middle, set sum along rows. Matrix sum. Okay, I'll leave it as it is. Then you have okay. Click on vector scope, okay, and set input domain is equal to frequency, okay, and amplitude scaling frequency is in hertz. That's fine. And your amplitude scaling, I don't see amplitude scaling in here, so x axis scaling, okay. Inherent, okay, frequency limits, magnitude, okay. So I didn't get anything. Let me see what's the error. Okay. For example, if we take this sum out and we connect them directly, there you go. You have an FFT plot. Of frequencies between so I have to scale the amplitude of the scope to see why it is out of range, but frequencies are there. You can see in y-axis is magnitude. If we do it in dB, frequency does it auto. Yeah, that's fine. Okay. So the two spikes, you can clearly see they are, one is at 15 and other is at 40, right where 50 is, right next to it. The scale, because of scaling problem, okay, I've magnified that, so right in between here you have 15, one spike of frequency, another one is at 40. It should be able to, we should be able to see it, but let me change the properties, display properties, grid persistent, axis properties, magnitude. I'm increasing the limit to -20 and 20. Apply, okay, run. Yeah, you can barely see it, so let me change it again. Magnitude, so let's do 80. Okay, oh, it does increase in the negative side. No, I wanted to increase in positive side, so while limit, minimum while limit, no, minimum while limit can be 20, sorry, minus 20, and this should be about 90. Yep, now it's very clear. So you can see two spikes, one at 15 and one at 40 Hertz. So this was a Matlab simulating example to do your FT plots.